Okay, so I think last time we finished this, right? We finished the hydrogel. So the hydrogel, if you look at our last discussion, this is on how we could have a stimulus. This is an example that has stimuli on temperature. So if we take different temperature, which means here we have some temperature that can make gas or liquid. You can make liquid or gas. You will also change the property. It can be a hydrophilic or a hydrophobic. Okay. And then how we see the hydrophilic and hydrophobic, we can also look the temperature in this kind of thermodynamics within the Gibbs free energy, which we are going to look at the enthalpy and the entropy, right? And enthalpy, the delta H, and the entropy. So it says that at the conclusions, this gel will soluble at the low temperature, and then it will be insoluble in the high temperature. It's going to be hydrophobic, as we can see from this picture here. Okay. And as I mentioned last time, this is actually one application for so it wants to make the moisture, the gas, and make it into condensed water. Okay. So it wants to perhaps change the moisture in some environment and within this materials. Perhaps this could be like a membrane or maybe some filter. Okay. And then it will be going to have a condensation inside. So that's hydrogels. Okay, just a quick review. So what I'm planning today is having 2 more sections, and then I think we can finish the polymer spatial architecture, and then we can move on to polymer characterizations, which we are going to see how we can analyze the polymers. So before that, let me finish this part. So another type that is I think it's quite interesting for the polymer architecture is a block copolymers. Okay. So if you remember, the copolymers, we can have homopolymers, we can have alternating, we can have a random, and we can have a block. Okay. What block means? It means that we can make our polymers with some certain blocks that has different property. So we can have 2 blocks, so AB, 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 or we can have ABC, ABC, or we can have ABC and then BCA, and then we can randomize these three polymers. But we can made it up, and we can adjust, and we can actually synthesize. So block copolymers is what we call here. Example here, diblock copolymers, triblock copolymers, or we can have ABC type, or we can make it more ABCD, ABCD, or E5 type. So it just typically say that 2 or more different polymers with different chemical identity that join together. So this red one, you can make it into like perhaps like polystyrene or polyethylene, and then the other one is maybe another polymer, and we can join together. Okay. Through some process, we can join together. I think mostly the process will be using leaving polymerization or anionic polymerization, okay, for most process in block copolymers. Okay, so let's go next. So here, as I said, that the synthesis is possible through the anionic polymerization or controlled radical polymerization, or we can say that, if you remember, this is what we call the living polymerization. And how we can know that this will be successful, the synthesis will be successful, it is from the living characteristics. So if we can make the polymerizations, we can make sure that it's still living, which means we are going to parameterize through the concentration of monomers, if you remember the living characteristics. So then, these two polymers, so A and B, and let's say the red one is A, and blue is B. Okay. So through these two polymer, we can try to adjust, and we can make it into different shapes. For example, we can make it like a ring. We can make it like the red one is like a ring, and then it has branched out the B, and then we can make it alternate A B A B. We can make it just a tree, right? Tri-block polymers. We can make just two di-block polymers, or we can make it like a branch for the polymer A, or we can make like this, or other parts as well. What's the key to make this happen? And how we can see that later from these block copolymers, we can also make another interesting shape, three-dimensional shape. Okay. But later we are going to see. Okay, now if you look at the next page, there are some interesting formula that I wish not really going to be in detail, but this is just to show you. So what I want to tell you from this page is in polymers, we are going to see that sometimes we are going to see the separation, and then we can see some behavior when they separate. Now, if we remember, if you've taken physical chemistry or I think organic chemistry, I think physical chemistry, if you get I think this is physical chemistry, right? Or no? Mixing.
Thermodynamics.
Yeah, oh yeah, thermodynamics also physical chemistry, thermodynamics, they get this Gibbs energy for mixing. And then, of course, this will be very similar with this regular thermodynamics. So for mixing, we could see that for these two calculation, for these two formula, we could see that the more we could add, like for example, if you have two small molecules, let's say this is what you have. So this will be the Coulomb fraction. Okay, this is Coulomb fraction, and then Coulomb fraction. This is the second molecules, and then you have to add another part that is going to relate to the fluorine-Huygens interaction. What is that? I think we need another section, another chapter after this special architecture. But let's say the fluorine-Huygens interaction is the characteristic that is appear when you are trying to make a solution, polymer solution. Okay, just take that as a coefficient for now. Okay, and then look at when we have mixture of two polymers. Okay, we have it's very similar, but then you will see that this part is going to have some differences. Okay. This is the same, but what I want to tell you from this interesting formula is that this is degree. I forgot to mention this is degree of polymerization. So, what I want you to think within the polymer mindset. Okay, so let me write here. The conclusion from this just a small amount of formula here is polymer difficult to mix. Okay. We're going to see in different chapter before we go to characterization, how polymers behave in a solution, and why we need polymer in solution. Of course, we need that, especially when you need to characterize polymers. I'm not sure in chemistry, in basic chemistry, whether you are able to use the, I think, chromatography. I think basic chemistry. Have you learned in basic chemistry? Chromatography. Like you are using perhaps color, and then you dip some paper or tissue, and then you get the water going absorbed, and the color getting degrade into the paper. Did you do it? No. Oh, okay. 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 So basically, what we did in polymers is basically similar, but what we need is basically we need the solution, and how we mix the polymer will be very, I think, important. But here, what I want you to see from this just slightly introduction of this formula, this polymers is difficult to mix, right? Polymers are difficult to mix, and they tend to separate. Okay? So we are going to see that the polymers, in our case, the block copolymers, they have their own phase separation or phase behavior. So they tend to separate, and they have their own characteristic and behavior. Okay, so this is some list on this phase separation and phase behavior. Okay, so phase separation, it will occur when the constituent blocks, they have different chemical property, and they prefer not to mix with each other. So this is when, depending on the blocks. Okay, so let me write here. Constituent blocks have different chemical property, okay, and prefer not to mix with each other. And the phase behavior is dependent on the thermodynamics of the system. And sometimes when we try to mix these two polymers, they sometimes very immiscible. So sometimes if they have the same or similar characteristic, these two polymers. So if these two polymers similar characteristic, so they are going to be very easy to mix, or they are going to be immiscible. But then, if you complete the mixing, you will see that sometimes you will have this phase separation. Okay. What will be the implication of this phase separation? So the phase separation will determine what will be if you have block copolymers and you have another polymers. Okay. So imagine you have, let's say you have this A, and you have B, okay? So let's say the polymer A, let me draw polymer A in the left and polymer B on the right. So you have another polymer that is in one place, so this is A. So it has some chain, okay? So and then this is B, and with some descriptive length B. Some chain. So what this list telling you is this block copolymers, this A, is easy to be interacted or easy to be mixed with this polymer A. So this will be, oh, this is my friend. Okay, I will come closer. Okay. And this polymer B, also they could get into the blocks on this block copolymers because they have the same characteristics. Okay? So we could use this block copolymers as like a glue, And then what else do we have? And then okay. And then we could see that there are some factors that will affecting the previous process. Okay, so when we take into context, so let me draw again. It's A and B. Okay. Of course, molecular weight within each polymer, A and B, they will be important. Because if you have high molecular weight, which means they tend to separate strongly. And they tend to separate strongly. And then we have interaction parameter. This is to describe the behavior between blocks, that they are actually repulsive each other. And then we could see that the composition for A, B, it gives you different morphology. Okay, we are going to see, I think, later for different morphology and nanostructures. We will relate it to the nanostructures. Okay. Let me just summarize for a while, okay, what we have, just to make notes that what we have here. So suppose that you have, this is polymer. So we are having mixture of A and B. Since they don't get along so well, A and B, but they are on the same, we hope they can get mixed. Okay? But because the thermodynamically it's quite difficult generally, so they are just separated. Okay? So they are separated, and how they separated is because of their depends on their molecular weight and then their behavior, repulsive behavior between each polymers and so on and so forth. And then we introduce the block copolymers. So let's just put just a die block like this. So this is A, B, and so we have this block. And then perhaps all is joined together like that. And perhaps a conclusion from this part is the block copolymers sits at interface between A and B. And we can say that it might be compatible, so compatibility between polymers are possible. And then we can see that it will also increase interfacial adhesion, which correlates to increase in, mostly we can see generally in strength in the polymers due to block copolymers. Okay. So again, these block copolymers it could act as an adhesion or like a glue. And because of that, because of this glue, it will increase, at least in general, mechanical strength. I think it's easy to follow that. And then as a consequence, if you see what we have here, oh, this is just a further explanation on what we have. Okay? So we call the block copolymers here as a compatibilizer. Okay? Compatibilizer is, so let's say this is diblock copolymers. We have yellow and blue. So this yellow interact with polymer A, which is outside here, and B is interact with polymer B. So polymer B is on the middle, and polymer A is here. So what will happen is when we have polymer A, polymer B like this, we input these compatibilizers. This polymer B is going to be dispersed. It's going to be dispersed in more circle. Okay. So we could see that it could also adjust how the structure generally in the system. So you can see some mechanism I'm writing here. I hope it can be easily understood. So the yellow part it has more affinity with the polymer A, while the blue interacts selectively with polymer B. And during the mixing or compatibilization, the compatibilizers, they migrate to the interface and interact with the polymer component. So they migrate to the interface, which is here, and then it seems like this small compatibilizers, they get into here, okay, each one of them, or maybe more, okay, maybe like that. So imagine that this green is the block of polymers, and then they like worm eating apple. So they are taking some part from here and make it small, okay? And they taking another part, making it small. So this blue will attach to this, and then they're taking this B, and then because of the yellow, they want to separate. So they take and then separate and make it small particle like this. So it could act as a dispersant, and so it maybe when you have like this is too large, they make average diameter for all particles. So they can also act as a dispersant within this example. So this migration helps reducing the dimension, as I mentioned, of the dispersed phase. And so that's one example how we can make, or how can we use the block polymers as a compatibilizers for, in our case here, as a dispersant. Okay. Dispersant, let me write here to just let you know, dispersant. Okay, and of course, this is just one example. So you can see that this block of polymers, it could have like potential application in many ways. So we could see later that there are some structures that can be made up from this block of polymers, and it will also relate to the nanostructure. If you have interested in nanotechnology, one way to do it is using the block of polymers. Okay, so let me write here just notes. I already put interesting words in the bold. So block of polymers, it's increasing the interfacial adhesion, as I mentioned, between two dissimilar polymers, so polymers A and B, by acting as compatibilizers. Or if you want to write like a glue, that's okay, like a glue. Or interfacial edges. Or maybe in other words, if you're perhaps familiar with the surfactant, you could also think block copolymers like a surfactant. Okay. Let me write here, like a surfactant. Because at least block copolymers need to have two different polymers. Surfactant have two different hydrophilic, hydrophobic, at least, right? So it's similar to what this surface active agent. So it's like interfacial agents. And the role of a compatibilizer is to improve the interfacial addition. Okay. So this means that if we are using this glue, it will make the mechanical strength increase. So it's enhancing overall mechanical properties and stability of the blend of composite material. Okay, so we are going to see that this is actually going to increase the stability also. Okay. So the key component that is important is interfacial addition, and then it's enhance the mechanical property. Okay. And this is just another further elaboration that the block copolymers they are acting as a bridge. Okay, with one block, it's having strong affinity for one polymer, and the other one is for the other polymer. Just further description. I think we can skip this, and then to see whether we are having a good mechanical property, we are going to see the fracture mechanism. So this is just a glimpse on fracture mechanism in polymers. If you want to know more, I think it should be in another lecture. So fracture in polymers, there are three mechanisms, at least three. The first one is pull-out mechanism. This refers to the process where polymer chains they slide past one another. So just slide like that, and then you can pull out the polymer. So when you give stress, okay, this is going to be easily to be pulled out. So that's why we call it just pull out. So perhaps if this is, let me just describe this. Let's say we have two different material in a composite. So if you pull out, so you take this stress going over there. So you can see that perhaps this green one is the connection between these two composites, and it was easily pulled out. Or to be detailed, the slides will be also related to the frictional force. So that's one. Okay, so this is one for pull out. Okay, and then second, we call it scission. So this is coming from scissors, like cut to cut, which means that we are going to see the breaking or cleavage of the bonds or the component in polymer when we apply stress. So this example, this is pull out, okay, and then this is scission. So you will see that it's perfectly break the bonds. Okay, so let me here. So perfectly, let me So this is broke the covalent bonds. While the pull out, you will see that we still have something that is attached within this component. So the key for the scission here is the cleavage of the covalent bonds. Okay, that's the second. Let me write here, second. And number 3, that is, I think, the most interesting one in polymers, and this is only happen in polymers. So we call this third mechanism is crazing. Just a quick explanation for crazing. So we are going to see that, let's say we are going to see some stress here, going here, going there. When we pull out, sometimes, like if you can imagine like a sticky rice or sticky cake, and sometimes when you pull out, you will see that in the between there will be some point, okay? Some point like this. We call this is becoming like a fibril. Okay? We call it it's a fibril, and it's also elongated. Okay? It's also elongated. And sometimes they also getting into or affecting the property, because sometimes they can be plastically deformed. Okay. So let me just explain here first. Okay. So the crazing, they consist of these fibrils that reach the two surfaces, and then it occurs when polymer is subjected to stress, tensile stress. It's leading to localized deformation. This is, I think, the one that is important. Let me write here. So localized deformation, and then it's developed voids. So what will happen if we have void here? So the void will increase, or the void itself will bear the load because of this stress. Okay. So this will also make our judgment wrong, and our maybe sensors, when we deal with the observation and maybe tensile stress, that will be wrong judgment or wrong calculations because of the void. So we take force here, and because of the void, because of the notch, I think if you take some course in fracture in polymers or other fracture mechanics, perhaps, you will understand that this void will be affecting this force here, and affecting your sensors when you apply this into your equipment. So this will be, I think, in one way or another, the crazing will appear in polymers because of this void. Okay? And then we have the elongations. Okay? And of course, this will only happen in polymer because of this. We can have this elongation. So if we have material that viscoelastic, and then maybe perhaps it's a composite, and then some part of the composite contains elastomere, this will probably will happen. This will probably will happen. So before the fibril fail, the tensile goes up and up and up, and it's basically makes our sensor getting wrong in the calculations. So the load will increase, And we can say that this will be having abrupt increase in fracture energy. In another way, between this 1, 2, 3, we can see from this graphs, this is interfacial stress between two polymers. This is the chain density. This is number chain. So the more long chain you have, until we call it saturated chain. This is elastic deformation. So as long as you are given your tensile around here, it should be still in the elastic. But then this is area for pulling out. If you increase on the left part here, you can get an ideal scission or ideal break for the bonds. So you could get definitely how much stress you need to make this cleavage in bonds in carbon. Okay. But then if you are having more and more carbons chain and then giving more stress, you will get this crazing property. At least from this picture, you could see the differences between the pulling out, crazing, and the chain scission. So crazing, so-called crazing is if we see from the typical behavior from this graph, you can see that this crazing is actually a combination from the pull out and this scission. These two combined this. And why this goes up like in this part here? Because of the void that is happened because of the elongation of the fibril. So we could see that mechanical property increase because increasing or maybe because the increase, maybe I'm right, because the increase of interfacial area, as we see from the graph here, and then because of the compatibilization between two blocks of polymer. And let me write in brackets that the scission and crazing are necessary. Necessary because they make the stress on above the level. So if we make some new composite using compatibilizers from the block of polymers, one way we could make the system increase in mechanical property. And how it's increased because of the interfacial area change density, and then because of this scission and the crazing, they are necessary increase the mechanical property. Okay. Okay, some example here is the high impact polystyrene. So this is polystyrene, and then we have the polybutadiene. So this is, let me write here. This is the polystyrene, right? Polystyrene. And in the middle is we have the PB. Okay. So this high impact polystyrene, or we call HIPS. This is mix of polystyrene and polybutadiene. Or let me write, it's not exactly butadiene, but let me write and polystyrene block butadiene. So it has spherical particles from the rubbery polybutadiene in continuous polystyrene matrix. Okay, let's continue after the break. Okay, now we have here is the high impact polystyrene. So our HIPS, this is mix of polystyrene and the block of polymers of polystyrene and polybutadiene. And what's so special about this HIPS is they have spherical particles of the polybutadiene rubbery in continuous polystyrene matrix. What the implication of that is, if you could imagine that you have like polystyrene like that, okay, this is just a illustration, and you have polybutadiene and you have polystyrene here. Okay, so what is the implications? So because of the spherical particles within this middle part here, and maybe we can see another part as well, the rubbery of this polybutadiene is make these materials more tough. So I think better if I gave you the graph. Okay. So the polystyrene itself, if I graph. So if the polystyrene, only polystyrene, so this will be the graph, maybe around here. So this will be polystyrene. And this high impact, or there is another one, the more medium impact here. And another one is the high impact. It's almost the same, but it's longer. So because of the rubbery part of this red color, this butadiene, because this is rubbery, it makes the elongations a lot more distance for these HIPS, basement of tensile and the E. So the material, so it's hard material, but tougher. I hope you remember what the tough means. Tough in terms of material science. Tough means the area under the curve. So the more you have the area under the curve, you say the material is more tough. So the more it can withstand the elongations, like in a polymer or in a rubber, we say it's tough material. We are not, it's different. It's strong and tough. Strong materials depend on this tensile. We say the tensile strength, right? Ultimate tensile strength and so on, right? But if you say tough, we say the area under the curve. It's also proportional to the ductility. Ductility and toughness, they are somewhat proportional on this elongation. So we can make within this polystyrene that is hard material, but we can make it more rubbery, and we can make it in more applicable within for high impact equipment. Because if not, if you're just using polystyrene, then it will be broken easily. But if we make it more durable, we can make it more tough. Although maybe it's decrease the tensile strength, but in most cases, when you deal with with more and more tensile, it could withstand. Okay? It could withstand, and it has a longer life. Right? And then for mechanical stability, let me write here. Let me erase a little bit here. So for mechanical stability, there are increased number. So why this is tough in other words? So there will be increased number sites for crazing and yielding. Okay. Yielding is because of the rubbery materials, and crazing because we employ two polymers. Okay. We employ the polystyrene and polybutadiene. Okay. And then the rubber particles. It has lower E, right? Which means it gives you stress concentration. So in another way, we could see from this part here that in a whole or in general form, we could see that it is stable, mechanically stable. And that's why the name, hence the name is a high impact polystyrene. Okay, this is just an example of how we could employ the block copolymers and make it into a different shape, different structure. Okay. Okay. Now the next section, okay, I will talk about the nanophase separation. So before I'm going to show you the example directly, let me just give you some illustrations. So let me give you three cases. Okay, so first case, I give polymer A and polymer B. Polymer B is smaller. Okay, smaller. The length is smaller. And then case 2, they have the same length. And in case 3, A is smaller than the B. Okay. So we have these three cases. What kind of structure that can be obtained from this block copolymers? Okay. Let me give you illustration. For the case 1, let me make it. Okay, for case 1, since B is having small length, short length, so if you remember, the particle B will meet with another B, which is another length, short length, right? So short length move here, so we could see that it will be going to be immersed, and then you see that going to be like that. And if we zoom out, perhaps perhaps we can see some because we call it spheres. And then the second case, the same length, then perhaps this is, well, it's going to be grouped with each other, but perhaps because of this same length, that maybe this will be so it's also grouping for A and B. For they will find the one that is attracting, right? And if we see from zoom out, we are going to see something like a cylinders. So we call this as cylinders. So again, if you remember that this is similar behavior with the surfactant. And the third case we can make that perhaps we could have this kind of like a lamellar structure. I will explain what's the most important thing within this structure and how we define the structure. Okay, let me give you the conclusions, and then you can, I think, easily to write the notes. What's the difference between this? This is just a few examples. So the more complete one, if you see from here. Okay. So this is I took block of polymers but insert of surfactant. So you see that we have the hydrophobic block, hydrophilic block, okay. And then what's the important one here is the ratio. The ratio between the parts, okay, the red part and then the blue part. How much the ratio? So the important one is the length. The length of the blocks. So if we have more length within the blue one here, we have something like this, as we previously mentioned, the spherical shell or spherical, just a spherical structure. And of course, we could see also the structure, but I think for now, just focus on the name here. This is just, I think they are adding some details, but I think as long as you know what does it mean, okay, how we could see. For example, if this becomes our default, then if we make another one that has more red one here than this one, then it will be inverted. The blue one that is becoming the core, and then the red one would be the matrix. So we have a cylindrical shell, and we have a vesicle. So the more and more the red one is getting larger. Okay, so the shell here is getting larger, and then when it's going to be equal, you could see that it's going to be like a lamella, like a planar layer by layer. And then we have some inverted one here. This is inverted one from the cylindrical and also from the shell. So let me write here. So ratio is from the chain length of the blocks. So structure, the separation determined by relative length of two blocks. Okay, so just a quick summary. So phase separations, this is occurs when in thermodynamics we can say minimization of the interface and also maximization of the entropy. So if you have a components inside one of mixture, the individual segments they want to actually separate, but sometimes because of the chemical links, they cannot. So what we can do is we need to minimize the interface between them and then maximize the entropy. How to maximize the entropy? Usually with energy, with temperature, we can make it more spontaneous reaction. And then from these operations, we can see that we could develop a new structure, and then we can say that this is become the nanostructure, the new nanostructure that we can apply. Okay. Okay, I think this will be done. Just I want to add one more here, but I think I will skip this, and we can continue to the polyelectrolytes. So this will be the last part on the special architecture. So polyelectrolytes. So we have three different sections: the hydrogel, the block copolymers, and polyelectrolytes. Sometimes the terms can be, so for example, block copolymers can be applied to surfactant as well, also within this polyelectrolyte as well. So sometimes block copolymers, it has the polyelectrolyte. We can also treat them as a polyelectrolyte if they have the property. Okay? So what is polyelectrolytes? Polyelectrolytes, of course, it has an electrolyte as repeating groups. Okay, which means electrolyte means the charge. Okay, we have charge. So it can be positively charged or negatively charged. Okay, So if we see just a regular polymers, this will be just a random coil like we usually see, like a noodle, like I usually mention. But if we look on the charge one here, this is having a negatively charged. The polyelectrolytes, because of the negative charge around this side chain, the negative will repel with this negative, right? So it makes it stretch. So it will not randomly coil. So in nature, we can see that it can have stretch out structure, right? So because the charges, they repel each other. Okay. Just a quick comparison. And then we see some example here. This is three that example that is, I think, quite oftenly used, especially the polyacrylate here and this one. I'm not sure that one, but I think that one also. But I think this is mostly frequently used. If you are later maybe having some experimentations using some polymers, sometimes you will see in most labs that use wet chemical method, you will see a lot of this polyacrylate, which giving the polyacrylic acid or PAA. This is some example. And then we have a positively charged polyelectrolytes. This is not really oftenly used compared to the negative one, but still we can also use this as our sources for polyelectrolytes. Usually it has the negatively in nitrogen in this allyl amine. And then what's important here, or this is another just getting for all polyelectrolytes. Okay, what's so important about the polyelectrolytes is because of the charge. Okay, so the charge, it has some effect, okay, that will determine the physical chemical property. That will also depends on the particle size and also the polymers. So you can also say the charge will stabilize or destabilize a particle system. Okay, in a quick explanation, okay, before going to the right picture, let me just give you slightly. So if we have this negative charge, and then we have positive there, chain that attracted. So small polyelectrolytes, this will having a short chain, and because of that it has increased charge density. Before large polyelectrolytes, which it has more chain, what will be the implication? It will getting stuck with another particle here, So we can say it can be a flocculant. So this is large polyelectrolytes. So it has a long chain. In implications, it brings more particles together because of the long chain. Or we could say that it can be a source of flocculation. You see from what we have here, this is what I mean. Flocculation, so you have a longer chain, and it can also make a coagulation here, like this one here, which it will increase the charge density. But if you have with the same charge, it will be just an excess of coagulant, and it can be just act as a dispersant. So it will be dispersed. So it will be charged. So the patch here will be charged, or it can be a polymer bridging, or it will be flocculant. It will bring small particles together, or it's just a dispersant. You can just make this two in a distance because they repel each other. So it can be a coagulant, it can be a flocculant, or just a normal stabilizer if you use the same charge. Or if you want to add just like a surfactant, so if you have an oil, you could also employ this electrolytes like that, and then it will take off the oil. And we call the process as a solubilization. Okay, I think that one will be just a unique property on polyelectrolytes. I think this is last one. Just simple applications, or in a variety. We have we can use it for super absorber, flocculation agent like the one before, maybe in a waste treatment for water using the flocculant, and a concrete process, seawater desalination is also considered as a purification, a layer by layer deposition to make a nano material or using nanotechnology, and then nanocapsules for drug delivery applications, and also for energy as well. Okay, I think you can elaborate this and maybe look into one of them. I hope everyone submit the discussion assignment. Okay, last time. The salt gel is also interesting methods to make a nano dispersed materials, because it can deploy the inorganic materials using organic template. That's very interesting. Okay, I think this will be last one. So, as a summary, of course, this is just one line, but I hope you know to elaborate each one of them. So hydrogel is absorb water, basically, the one that is unique for this hydrogel. And remember that because it's a gel, it means that you cannot dissolve the cross-link, right? So you could just absorb water at some certain conditions, and then perhaps it's going to be releasing water. Okay? And then we can also have the block copolymers, which is going to be unique component or versatile component that can guide, direct, and then employ phase separation, and we can adjust and we make a new nanostructure from this block copolymers. And then polyelectrolytes, we can have different properties that are quite distinct because of the charge, amount of charge inside the polyelectron. So it's just a small subject, but I hope these three, if you are interested in one of them, you could try to look out and read more in more articles, especially if you plan to go into taking master program in maybe in polymers or maybe in another field, but it relates to polymer, perhaps within this tree construct, because it is quite interesting. This tree has special architecture in my opinion. Okay. So I think that's it for today's class. Okay. So we are going to see this Thursday. Or perhaps for this Thursday, I give you another assignment discussion about this one. Okay. I will give you perhaps about one of these three. Okay. And I think we just have 2 weeks left, but I think we can finish it on 2 more Monday class and maybe perhaps 1 more Thursday class. I think we can finish. Okay. So I think that's it for today. So see you later next Monday. Okay, next Monday.